Guy Davis is Senior Consulting Engineer Specialist at Juniper. I'll let you introduce yourself.
Thank you very much. So, good afternoon everyone. I hope you've all enjoyed your lunch. As Ian says, my name is Guy Davis. I'm a Senior Consulting Engineer in the SP Cloud Centre of Excellence at Juniper Networks. I've been with Juniper for about 11 years, but working on internet service providers, systems integrators, and then vendors for closer to 25 years. So, as Ian said, this is kind of a fundamental question. Where exactly is the edge of the network, or where should it be? So, I guess that the starting point is most of us in the room are familiar with the challenges that service providers are facing today. You have a 45 to 55% compound CAGR growth in your data. You have very few opportunities to leverage the traditional markets that you have sold to, because the over-the-top providers are basically delivering the same services using free or ad supported models. And you're being driven towards reducing OPEX as a mechanism to protect your margins. This is kind of driving you towards utilizing the kinds of features and tools available to the IT organizations, using cloud, disaggregation of your applications and your networking equipment, virtualization of those objects, and trying to make use of analytics and automation and artificial intelligence in order to be able to better utilize the assets that are available to you. And what we're kind of seeing today is with both the standards approaches and the operators themselves are moving away from a centralized model where all of your networking assets, all of the intelligence is in highly centralized, high volume, high capacity platforms in very few locations around your network. But obviously that kind of model is leading to challenges with scaling those platforms to meet the kind of requirements that your customers are presenting to you. So what the distributed telco model provides is the ability to take the applications and move them towards the edge of your network in order that you can mitigate some of the challenges associated with scale by reducing the scope of coverage of each of those instances of the applications. And whether you do that using MEC or CUPS or Core if you're in a fixed environment, that kind of doesn't matter. The key is that you're driving the application further and further towards the subscriber in order to gain the advantages, as I say, of enhanced scalability, but also within the 5G environment in particular, to meet the kinds of latency demands that are being placed on the network by the protocols themselves. So what we see is basically you have the RAN is kind of moving in towards the centre of the network, whilst at the same time you've got the data, your applications, your user control moving out towards the edge of the network. And what you end up with is a requirement for a platform that can deliver the RAN applications, the user applications, and the core functions, the core networking functions, distributed out towards the edge of the network. And what operators have told us is that they would like to be able to optimize the location in which those applications are delivered on a per user, per application, per slice basis within their network, which means that they're going to have to deliver edge functionality in potentially a number of locations within a somewhat hierarchical network. The key to delivering all of this is kind of a unified DC model with MPLS WAN infrastructure delivering you an IP fabric over the top of which you can have a unified SDN, so software-defined networking control layer to deliver the necessary virtualized networking functions and connect those functions to the real network, both at the subscriber access side and at the core side. So, as I mentioned, what we're seeing are demands for distribution and virtualization of of access functions. So that the RAN, the FTTX, the mobile access, the ability to perform network slicing being driven from the RAN edge, the radio edge, in towards the center of the network with techniques such as CRAN, whilst at the same time we're seeing the core functions such as VEPC, the MME. There are certain functions that remain in the GI LAN which need to be centralized, and others which you want to distribute. So the key drivers, I guess, to distributing what must be distributed tend to be low latency, the ability to deploy flexibly and in highly granular fashion, so per slice, per subscriber potentially, the ability to deliver highly available applications using cloud-based techniques rather than building pure carrier-grade solutions. What we see is customers looking to build cloud-based high availability. So stateless applications, rather than replicating state between copies, replicating capacity and having state maintained either in shared databases or even state created at the time the subscriber reconnects to the application to use the newly available function. One of the interesting drivers that we've seen, particularly in the area of IoT, is battery life. By reducing the RTT of IoT objects to the application that they are using, we've actually done some work with one of our service provider customers, and we calculated something in the region of 50 to 100% battery lifetime extension on an IoT object. Now, if you've got an IoT object that numbers in millions, where each time the battery dies, you have to send someone out to actually repair that or replace the whole object, and you can extend its lifetime by 50 to 100%, the return on investment is effectively instantaneous. You know, we said these numbers to the guys in the IoT organisation, and it's like, yeah, when can we have it? This is what we need, because this is one of the key drivers to the cost model of deploying industrial and B2C type IoT models. So one of the interesting discussions I actually had with a colleague of mine earlier was in the area of local breakout, because when we talk about local breakout, often we kind of wave our hands in the air and say, what we can do is move the breakout from the core out to the edge, and it will magically go out onto the internet at the edge. Well, that's kind of true if you've got peering with your upstream providers at every single one of your, I don't know, 2,500 aggregation sites, your core central offices. I'm guessing that's not the case. So you are still going to have to bring that traffic back across probably exactly the same infrastructure as you used to deliver the traffic, whether it's GTP encapsulated to the packet core, or whether it's native IP packets, and deliver it straight to the internet gateway. The chances are you're still using the same backhaul capacity to deliver that function. And the only saving you make in that particular instance is the ability to offload capacity from your centralized user plane of your packet core. So when we talk about local breakout, it's an interesting function. It's particularly interesting if you have the application terminating at the local site. But if you're talking about local breakout to the internet, the models aren't quite so interesting, shall we say. So with respect to MEC, what we're seeing is that we've heard our customers talk to us about various different locations in which you could deploy MEC. And these range from in an enterprise site, delivering MEC to small cells within the enterprise. I know that Jason Dye, who talked this morning about the industrial application. I can see that functioning very well in that environment where the industrial application is delivered over small cells. You have a very local application server delivering your functionality with the ability still to go to the core for other functions. We've also heard customers talk about delivering MEC as part of the ENO-B. That's certainly going to give you optimal latency advantages, but in our work we've come to the conclusion that the numbers of devices that you would have to deliver, the life cycle and the cost lifetime of devices that live at the base station tends to be of the order of 7 to 10 years, the write-off period. That is not a compatible life cycle period with, you know, x86 hardware. The churn on x86 hardware is more like 2 to 4 years, and that's the write-off life cycle that you tend to get with traditional IT equipment. Where we've been focusing our approach has been at the aggregation point, primarily because it gives you the best optimization, or the best compromise between the numbers of locations. So, you know, if you look at the UK as an example, take the big operators in the UK, they've got maybe 25, 30,000 base stations in the UK. And there would be of the order of 2,500 aggregation sites. So if you're talking about 2,500 aggregation sites, most of which are deemed secure, versus the base stations which are deemed insecure, most of which have data center style capacity, heat, cooling, power, the space for 800 mil deep servers. These things all guide us towards making the proposition that the edge of the network for MEC is in an aggregation layer. You get the best compromise between the cost and the operational cost of replacing and updating hardware versus the latency benefits, where, you know, in general, the aggregation site, which has maybe 10 to 20 node Bs, you'll be 2 to 4 milliseconds away from the base station. So, one of the other interesting questions, which I'll try to, I've been given my 5 minutes already. Our view is that CUPS and MEC are complementary. They're not necessarily competitive, although they do have a degree of crossover. There's certainly circumstances in which you would wish to deliver a complete VEPC nearer to the edge, or indeed parts of the complete VEPC, and those parts could be delivered both as a software element there, so you can deliver using software, which gives you greater flexibility, greater speed of deployment, versus a hardware built-in deployment where you've got, for example, the S-Gateway user plane in your underlying hardware device, with the ability, you know, you need those hardware devices out at the edge to be able to actually transport the traffic. You know, they have to be there, so integrate with them and you get the advantages of higher speed, but you've got slower deployment cycles, etc. So within our context, we already deploy multiple multi-layer networks with both Contrail in the RAN and in the core. The virtualized core, we're able to use Contrail. We have for many years deployed MPLS as a virtualization layer, if you like, to maintain separation of resources within the core network, the backbone network to mobile operators. But the whole key is that everything is delivered over the top of a standards-based layer 2, layer 3 VPN platform that is highly robust, highly reliable, and highly trustworthy. Excuse me. Just a quick pointer on Contrail. I think everybody will get these slides at the end of the day, so I'll let people read. I'll be around today. Unfortunately, I'm not around tomorrow, but if anyone has any questions on how Contrail works in conjunction with OpenStack and with real physical networks, then grab hold of me and I'm more than happy to discuss that. And one of, I guess the key point that we would like to make is that it's all about open platforms allowing us to make allegiances, alliances with partners who can deliver the best functions within the context that we want to work. So, you know, I've named a few there, the people that we're working with actively. I think but the key is that when we work with these organisations, we're doing so through open APIs, we're doing so based on the top of OpenStack, you know, using all the familiar platforms that everybody's aware of. So at that point, I will stop because I think I've overrun fractionally and ask if anyone has any questions straight away.